remember on Monday we focused on work, kinetic energy, and we didn't even mention potential energy, right?
Yeah.
We did work, power, kinetic energy. So chapter 7 is work, power, kinetic energy, and then the work energy theorem. Work energy theorem, which says work, the definition of work is force started into dr, right? And then you have power is force started into velocity. Then you have power is work divided by time. Then you have kinetic energy is 1/2 mv squared. Then you have work is equal to change in kinetic energy. So far that's sort of the summary of chapter 7. Then you have work of gravity. Remember, gravity only cares about the vertical height that something rises. So we can say the general equation for it is negative mg delta h. Right, so that means if something goes up, its height increases, then the work that gravity does is negative. If something goes down, its height decreases, then the work gravity does is positive. And the work of a spring is equal to what? 1/2 kx initial squared minus 1/2 kx final squared. And if x final is positive, if x final was 0, then you just have this thing, right? So we did a problem like that. And then the work of friction is negative mu k n d. Okay, now let's talk about chapter 8, introduces conservative versus non-conservative forces. The concept of conservative versus non-conservative forces. So definition is that conservative force is a force that the work done by the force is path independent. The work done by a conservative force is path independent. So that's one of the definitions or properties of a conservative force. So the most obvious example that we're dealing with here, it would be gravity. So if I take this object, the folder, and I go up from here to here, gravity does negative work, right? Negative some amount of work. Then if I start from the same location and if I go at an angle from here to here to the same height, then I go straight to the same position. How much work does gravity do now? Same or more or less? So if I start here and end there, versus I start here, go like this, and go like that, but end at the same location. Does the work gravity do change depending on the path?
No.
The answer is no. It's path independent, because the work gravity does is negative mg delta h when you're going up, right? When you're going at an angle, gravity doesn't care how much you go horizontally. Then when you go straight horizontal, gravity does no work at all, right? Because mg, and then the displacement is this, right? The angle between them is 90. So when you go straight, gravity doesn't do work at all. So gravity says, as long as you start here and end there, I don't care how you get there, the work I'm gonna do is always negative mg delta h. So gravity fits into this pattern, right? 2, the work done in a closed path is 0. So that would be a sequel to that, right? So if you start here and you go up, gravity does negative mgh, right? Then you come back down a different path, you go like this and then you go like this, right? Well, gravity says, I don't care what path you take. You started here, you ended there, then you started here, you ended there. So the total work I'm going to do is 0, right? So the total work done by gravity is 0. So one practical example of that is if you're, let's say, trying to get some exercise, and you are in your bike, and let's say you started your house, and you're biking, you know, and then in your bike, let's say near your house, there's a road like this, then there's a road like that, right? And let's say you go something like this. That's pretty steep, huh? Okay, and then let's say there's another road that just goes like this. And it's the same height as that one over there, you know. So the same level. Okay. So, you know what, let's just say, I'm just gonna cancel this portion of it. Let's just say like this. Like this. I'm gonna go more like this. Okay, that's a better illustration. Okay, so now if you want get some exercise, which one is better exercise? Well, in terms of calories, you're going to burn the same number of calories either way, right? Because calories is a measure of how much work you had to do against gravity, right? So in other words, if gravity is doing negative work on you, you're doing positive work against it, right? So by making this thing go up, gravity is doing negative work, but I'm doing positive work, right? And then when I lower it, gravity is doing positive work and I'm doing negative work. Am I burning calories both going up and down? Yeah, because going down, I'm fighting against the tendency of the folder to want to accelerate, right? So I'm still burning the same number of calories as I do going up. But I'm just doing negative work in the sense that gravity is doing the active part of the work. I'm fighting against gravity so it won't accelerate, you see? But I'm still burning the same number of calories going up and down. But I'm using a different set of muscles in going up and down. But calorie-wise, same number of calories. Okay, so now, if you're going straight, are you doing work? Well, there's probably some friction, so you're doing work against friction, okay? Then going up, you're fighting against gravity, so you're doing positive work. Okay, over here, you're doing constant positive work, right? So the total number of calories burned both ways is the same. So which one would you do? Well, I would probably choose this path because I can't do very steep, right? So the difference here is that the power output is larger here. You're doing a large amount of work in a short amount of time, or at least you're trying to do it in a short amount of time, right? Whereas here, you're doing the same work laid out over a longer time. Which one do you guys prefer? Which going up which way? Huh? Left one? Would anyone choose the right scenario? Yeah, because I know why some would choose the right. Because you say at least majority of the distance, I'm relaxing and just thinking about whatever. And I just have a short amount of time where I gotta do a lot of work. So I'll put up with that. Here, I'm not enjoying my ride at all. You know, I'm just constantly having to do work, right? So the conservativeness of gravity means it's kind of up to you which path you want to take. You're going to do the same amount of work anyway. So it's just you get to decide whether you want to lay the work out over a long time, right? Or you want to do a short time, very quick, a lot of power output. So the power here is much greater than the power there because over a short distance. Now, if you take a roundabout path, let's say you go like this, level, and then the road goes like this, the road goes like this, then comes back, and now you can go down, right? So then you go back to your house. Now which path do you take? So now you say, well, the network I'm gonna go do like this, then when I go down, I'm gonna do negative work. I'm gonna still burn the same number of calories no matter which close path I take, because the total work I'm gonna do is 0. Does that mean you burn 0 calories? No, the total work is 0, but burning calories, you burn calories doing negative work and positive work. You see? So when you lift something and you lower it down, like a barbell, you don't burn calories? Oh, definitely you do. In one rep, you're burning twice the calorie as just lifting it. But the net work you do is 0. Isn't that weird? But the burning calories, you double the work. You double the work of one path. So now which one would you choose? Well, depends. If you go this way, you say, I get to enjoy most of my ride. I do, this one is gonna be hard, but I'll put up with that. Then I'll go like this, I'll come back, and then I'll have a nice long distance to come downhill, right? Now if you go this way, okay, it's not gonna be too hard. Then I'm gonna go like this. I'm gonna really enjoy it, but for a very short time. And plus, you know what, this might be dangerous to go down on a bike, you know? So I think most people would choose the right path this time, you know? I still wouldn't choose the right path because I have a torn meniscus, you see? So you don't wanna go up torn meniscus like this. I could do that maybe, but this one I couldn't. But most people would probably choose this. But that's again a matter of not so much physics as a matter of preference of how you like the ride, you see?
That's why they have gear ratios on bikes.
Huh?
That's why they have the gear ratios on bikes.
Yeah, exactly. Then the gear ratios of the bikes, yeah.
The power required on a steeper incline.
Of course, if your bike doesn't have any gears,
Yeah.
don't do the steep one.
Yeah.
You know, you need a lot of good gears on that. When you do races like such as the Tour de France, do you get to decide, let's say if they have a closed path, do you get to decide, I want to go this way? Oh, no, I actually rather go the other way. Can you decide? Or they tell you you have to go this way? Yeah, you have to go the path that they chose for you because maybe they want you to go up a long, shallow road, but they want to see your persistence. Can you maintain that for many miles? You see, so they want to see some skills from you, right? So you don't get to decide, oh no, I'm going to go the other way, you know. So then, how is this connected to anything we're learning? Well, because of these two laws and Green's theorem, which you learn in the end of Calc 3, right? Then we can connect the concept of conservative forces to potential energy. So that's how calculus 3 comes in. Conservative.
Wherein the work done by that force on an object only depends on the initial and final positions of the object. In other words, the work done by a conservative force on a mass does not depend on the path taken by that mass. If the work done by a force follows this rule, then we call it a conservative force. For instance, the gravitational force on a 5 kilogram mass is 49 newtons. If the mass moves downwards by an amount of 6 meters, the work done by gravity is going to be 294 joules. Now let's start over. Say the mass again moves down 6 meters, but then it moves up 6 meters, then down again 6 meters. The work done by gravity for the first downwards trip was 294 joules. Then for the upwards trip, since the gravitational force is pointing in the opposite direction of the motion of the mass, the work done by gravity is going to be negative 294 joules. Then for the last trip downwards, the work again is positive 294 joules. That means that the total work done on the mass from gravity is still 294 joules, just like it was when the mass was lowered only once. In other words, the work done by the gravitational force doesn't depend on the specifics of the path taken by the mass. The work done by gravity only depends on the initial and final position of the mass. In fact, you could allow the mass to take any path from this initial point to the final point, and the work done by gravity is still just going to be 294 joules. Because the work done by gravity doesn't depend on the path taken, we call gravity a conservative force. The force exerted by a spring is another example of a conservative force. The total work done on a mass by a spring does not depend on the path taken by the mass. It only depends on the initial and final positions of the mass. The term conservative comes from the fact that conservative forces conserve mechanical energy, whereas non-conservative forces do not conserve mechanical energy.
Yeah,
Mechanical energy is kinetic energy and potential energy. An example of a non-conservative force is friction. If I move a mass along a table from point A to point B, friction does a certain amount of negative work on the mass, which creates some thermal energy. If instead of going straight from A to B, I make the block go from A to B back to A over and over again, the work done by friction will become larger and larger, and it'll generate more and more thermal energy. Because the work done by friction depends on the path taken, friction is not a conservative force. Similarly, air resistance is not a conservative force, since the work done by air resistance depends on the specifics of the path taken. It's useful to note that if a force is conservative, you could define a potential energy for that force. That's why conservative forces like gravity and spring forces have potential energies associated with them, and non-conservative forces like friction do not have potential energies associated with them. This makes sense because if you do work against the gravitational force by lifting a mass in the air, you can get that energy back out by letting the mass fall down, turning potential energy into kinetic energy. Similarly, if you do work against the spring force by compressing a spring, you can get that energy back out by letting the spring decompress, which turns the stored potential energy into kinetic energy. But if you do work against the force of friction, you'll have a hard time trying to get that energy back out. The energy has been dissipated into the form of thermal energy and is now randomly distributed along the ground.
Very good.
Into the
Very
block.
good explanation. So, see, conservative forces conserve energy. Very well said. Conservative forces conserve energy. By doing work on it, you store energy in the form of potential energy, you see. You lift this, you do, so now we say it has potential energy equal to mgh. Right? Then you lift, you let it go, that potential energy converts into kinetic energy. Right? But if I move something laterally across the table, friction does negative work, but I haven't stored that energy. It goes into thermal energy. You see? Okay, so the formal mathematical expression is a force field defined everywhere in space or within a simply connected volume, so it's called a conservative force, if it meets any of these three equivalent conditions. The curl of F is the zero vector. There is a zero net work done by the force when moving the particle through a trajectory that starts and ends in the same place, right? So in other words, the closed line integral of the force is zero, see? So that's what it means to say the work done in a closed path is zero. Work is equal to F dr, that's equal to zero, and then the curl of F. This is, when do they learn this in Calc 3? Way at the end of Calc 3? Mm-hmm. Yeah? You guys are all in differentials, right? Differentials and linear? You didn't know that's the actual unstated prereq for this course, right? Unstated, right? So the curl of F is zero, and then the force can be written as the negative gradient of a potential. Or we could call it U or phi. This phi, what's the meaning of it? It's the potential energy stored in the force, right? This is a scalar field and this is a vector field. The vector is the derivative of a scalar, right? It's a gradient of a scalar. So F is equal to negative du dx I hat. Is he following me? So that's a conservative force. Now follow me. Okay, good, good, nice. Du dx. What happened? Was it a black hole? He disappeared? Oh, okay.
Finished.
I looked up and it's like, he's gone. Okay, so now, if it's a 2 or 3-dimensional vector, then you take the partial derivative, right? Minus partial u, partial x I hat, minus partial u, partial y j hat, minus partial u, partial z k hat. Right? And then the meaning of this concept, scalar field, is potential energy. How do we know that? Well, if this has units of newtons, do a unit analysis. This is, if we didn't know the units of this top numerator, we put a question mark, and then the units of the bottom is meters. Right? So what's the units of that potential field, the scalar field? It's Newton meters, which would be a joule. You see? So that's a proof that this scalar field, which the force is a derivative of, is the potential energy stored in that force. You see? So the term conservative force comes from the fact that when a conservative force exists, it conserves mechanical energy. So the same way that the video said. The most familiar conservative forces are gravity, the electric force, and in a time-independent magnetic field, and the spring force. Right? Many forces, particularly those that depend on velocity, are not force fields, such as friction, air friction, surface friction, right? They depend on velocity. In these cases, the above three conditions are not mathematically equivalent. So let's see here. For example, the magnetic force satisfies condition 2 since the work done by a magnetic field on a charged object is always 0, but does not satisfy condition 3, and condition 1 is not even defined. The force is not a vector field, so one cannot evaluate its curl. So that means the magnetic force doesn't have a potential energy. It's different than the electric force. You see that? It says, so the magnetic force, it says, is not in reality, it's not in reality a force field, but the electric field is. Magnetic, so it's gotta satisfy these conditions. You see? So accordingly, some authors classify the magnetic force as conservative while others do not. So it's probably a debatable debate going on. But then of course we combine magnetic force and electric force and we call it electromagnetic force. You know, and that's one of the four fundamental forces of nature. So
But you could push two magnets together and it'll act like a spring and shoot it back out.
that part, it's probably looks like a conservative, yeah.
But I can see.
Because it says that it meets condition 2, but not satisfies condition 3. In other words, there is no scalar field that can be said to be the derivative of the, whose derivative is the magnetic force. So, the magnetic force is an unusual case. Most velocity-dependent forces, such as friction, do not satisfy any of the 3 conditions, therefore are unambiguously non-conservative. Examples of non-conservative forces are friction and non-elastic material stress. Despite conservation of total energy, non-conservative forces can arise in classical physics due to neglecting degrees of freedom. For instance, friction may be treated without violating conservation of energy, and so on and so forth. So it goes deeper and deeper, right? So the idea is that for those forces who are true force fields and they have a gradient, then instead of talking about the work that the force does, we can talk about the potential energy stored in that force instead of talking about the work, right? So remember from Monday's equations, we had this equation. Work total is changing kinetic energy. And on Monday, we didn't even refer to potential energy. So if we had the gravity doing work, we left it here, work of gravity. If we had the friction doing work, we added that to that. If we had the spring doing work, we left it here. And if we had an external force pushing on the object, we left it on the left side. Work external. So work external can be somebody's pulling on the object, you know. So now what we do, if we want to instead doing it with potential energy, we replace work of gravity by what? The work done by gravity is going to be integral of the, let's see here. Let's see, if the gravity, let's see, work of a conservative force is what? Integral F conservative times dr, right? But then F conservative is what? F conservative is going to be negative du dr. Negative du dr times dr. Right? So the work for all conservative forces are going to be what? Dr cancels. Work of a conservative force is equal to what? Negative the change in its potential energy. You see? So in other words, if I lift something, and it starts here, if I lift something, let's say I do 10 joules of work. I do positive 10 joules of work. Gravity does what? Negative 10 joules of work, right? So what's the potential energy that is stored in the object when it's here? Negative of the work done by the gravity, which is gravity does negative 10 joules, negative of negative is positive. So the potential energy stored in it is 10. You see? So that means the work that the conservative force does, if it's negative, then you store positive energy into the object. Then if I let go, now I'm not doing any work. Gravity is doing 10 joules of work. Right? So now this is 10. The loss of potential energy is what? 10 joules. Where does that loss of potential energy of 10 joules go? Into kinetic energy. So by the time it hits the ground, it's got 10 joules of kinetic energy. You see? And then where does that kinetic energy go after it stops? Into sound and heat, right? Created sound, didn't it? So it creates sound energy, and also the molecules of the table and the folder get a little bit hotter. So ultimately that 10 joules goes into the air, and it goes into sound energy, and then the net is 0 total, right? So all of life is really a transformation of one energy into another, right? How do we walk? We get the energy from food. Well, where does food come from? From the soil, from plants, from animals. Where do those get their energy from? The sun, you see? And where does the sun get it from? Well, the initial gravitational potential energy collapse of a nebulae, right? So the nebulae starts really big, gravitational potential energy decreases as it goes down, creates chemical energy, right? And then the sun gives off that energy, then goes into plants and animals, then we eat that energy, then we can walk, we can go to school. When you go to school, you learn a bunch of facts. That's units of energy that you're acquiring, you know? It's making your brain more systematically, more analytical, and that's a process of you getting more, acquiring more potential energy, chemical potential energy in the brains. Now you're able to do programming. Now you're able to learn math. That's how the universe works, right? Ultimately, we are the universe's attempt at understanding itself. That's what we are. We're little bits of energy that's trying to understand where it came from. Now we're going into philosophy, right? What's the meaning of life? Right? So the universe said, here's all that energy I have. Here, I throw it out to you. Now all those little bits of energy, now start learning, acquiring energy, and learn about me. So in order to learn about me, you gotta learn all this math, you gotta learn all this knowledge. So you're doing all this work, right? To go to school, to get an A. All the work that you do is just basically, you're giving it back to the universe, what it gave you, you know? Transformation. And then once you've acquired all that knowledge and skills, you go interview for a job, and the job says, okay, your starting salary is $100,000 unit of energy. Money is a unit of energy. You see? So literally all that's happening is just one form of energy into another, like lifting it, how I lifted it, chemical energy. Then it went into potential energy. Then you dropped it, went into sound energy, went into heat energy. Well, life is all about transformation of energy. You're learning, that's kind of energy. Knowledge is energy. Wisdom is energy. Skills that you're acquiring is energy. Then you go make energy, you make money. With that money, what can you do? What's money good for? Well, if it's just sitting in the bank, it's good for nothing. All it is potential energy that's unrealized, right? With that money, you can now purchase a home. That's kinetic energy. You purchase the home. Now that's another form of potential energy. You can go live in that home, you can have a comfortable living, but if you just live comfortably and say, that's it, no, you gotta keep doing something. You gotta now say, I gotta fix this, I gotta fix that, you know, just transformation. Now what should I do with the rest of my money? It's sitting in the bank. Let me put it in an investment, so I raise my potential. Well, what's an investment? Investment is a bunch of other people trying to do what you're doing, making the best out of their money, you know? Then you put it in investment, then you pull out of that investment, you say, I need to go travel the world. You put it into kinetic energy of the airplane. You know? Then one day when you die, your energy goes and dissipates into the ground, right? Sprinkles all into the ground. Eventually, when all the populations and the people are all dead, part of the people that are living here are going to go to live around the star Alpha Centauri A, our closest sun-like star. And we have discovered another extrasolar planet there. So our potential energy drives into the kinetic energy of the rocket, goes, makes new people there, and they keep surviving and carrying forth that energy. What's the purpose of the whole thing? That's what we're all here to figure out. There's no easy answer. Right? We're understanding what the purpose of it is, and we're in the process of understanding, and we don't know, you know. But it's all potential energy, kinetic energy, all of this. And money is a form of energy, you know. Okay, so then what do? We take the work done by gravity and take the work of spring, and if there's any other conservative forces here, we write them as negative the change in potential energy of gravity. Work of friction, I can't say that because there's no potential energy for friction. How about work of spring? Oh yeah, negative change in potential energy of spring. Plus work external, no, that's somebody pulling it or pushing it. No energy with that. So then work external. Then I'm going to take this negative change in potential energy and negative change in potential energy of the spring, and I'm going to put it on the right side of the equation, right? So then I'm going to say work of friction plus work of spring is equal to what? Oh, no, sorry. Work of friction and work of external is equal to what? Change in kinetic energy plus, and then see this one goes to the right side, becomes positive. See? And then this one goes to the right side and also becomes positive. So then you have change in kinetic energy plus change in potential energy. And then that becomes kind of like that equation. Let's see here. Let's see if there's any other good source here describing this. Something a little bit more. Yeah, they kind of do it here a little bit. The idea that I want to develop is a bit similar to this. So the idea that I want to develop is that I want to say work friction, work external, and if you have any conservative forces, you don't even ask what's the work done by them. You put it on the left side, on the right side as a potential energy. And then potential energy plus kinetic energy is the total energy of the system. And that total energy is usually called mechanical energy. Okay? So in other words, you have now two forms of the work energy theorem. One form is to say total work done on a force is the change in kinetic energy. The other way to say it is that the work done by an external force plus work done by friction is equal to what? Change in total energy, which is sum of the kinetic plus potential. So we can call this one the first form of the work energy theorem. And then we can call this the second form of the work energy theorem. Okay? So whenever we see a problem involving work and energy, we can choose to decide which form to use. Okay? So take, for example, something like this. Something as basic as this problem. Let's say you have a spring that's curled and the spring constant is 40 newtons per meter. And let's say there's no friction. And so now this is compressed by 0.3 meters, no friction. So then the block comes, the spring uncoils. By the time the block reaches the equilibrium, the spring releases the block. So what's the final velocity of the block? The final of the block when the spring releases it. Okay, this is a pretty simple problem. I mean, something that even Physics 11 students should be able to do, right? Physics 11? Because it's just a spring, no friction, nothing. But then how would you approach this from this point of view or versus this point of view? Okay? With this point of view, you would say total work done by the on the object. Well, what are the forces doing work on the object? Spring is doing work. Is there any other force doing work? No, right? And then that's equal to the change in kinetic energy, because gravity is not doing work, normal force is doing no work, right? And if there's no friction, friction is doing no work. So then we have work of the spring is equal to its final kinetic energy, okay? So then what is the work done by the spring? Remember the equation is half k x initial squared minus half k x final squared, right? Wasn't it that? Remember Monday we derived that equation? It's the integral of negative kx dx from x initial to x final, right? But then in our case, x final is 0, right? So then we just go like that. Then we have here half of k x initial squared, half mass of the block, v final squared. So it's pretty simple. Then you just do 20 times 0.3 squared. It's going to be 0.09. 20 times 0.09. 1.8. Square root of 1.8, right, is the V final. Now, how would you approach it from the second form of work energy theorem? So now you would just say, is there a friction? Is there an external force? Is there somebody pulling it? No. Is there friction? No. So the net work done on the system is 0. Oh, you see that? Nothing else that did work. There was no external force, there was no friction. So in this way, you just say 0 work done on the object. Whereas with this way, you say, oh yeah, spring does work on the system. You see? But then here on the right side, what do you have? Change in total energy, which is what? Kinetic energy final plus potential energy final minus kinetic energy initial plus potential energy initial. Right, that's what I'm doing here. The total energy of the system. So the total energy final minus the total energy initial. Okay? So then you say, that means the kinetic energy final plus potential energy final is kinetic energy initial plus potential energy initial, right? That means the total mechanical energy of the system is conserved because no energy is lost to heat. You see, there's no friction. So what's the initial kinetic energy? 0. What's the initial potential energy? Oh yeah, there's potential energy stored in the spring when it's compressed. What is it equal to? Half kx squared. see that? It's so different now. You see? And then here you say, okay, what's the final potential energy? There's no potential energy at the end. What's the final kinetic energy? Of course, the final answer should be the same. You see? Which system is better? Or is there a better or just a matter of preference, I guess?
Depends on the question.
Huh?
Depends on the question.
Depends on the question. So is it better to say, oh, you know what, there's no work on the system. There's no net work done by friction, right? So then energy is conserved. And therefore, you do it from an energy conservation view. Here you say, oh no, you don't even talk about energy conservation here. Here you say total work done on the system, whether it be gravity or anything, total work is changing kinetic energy, right? So then you say the spring does work. That's equal to the change in kinetic energy of the object. Okay. So now let me do a similar example. Let's do it both ways. See which one we like again. So now I'm going to release the 2 kilogram block from the air. 2 meters. There's a spring. So the block is 2 meters from the top of the spring. I let go and the block comes, hits the spring and compresses the spring. What's the final compression amount in the spring? Okay, how do we answer that with the first form versus the second form?
So the first one, that's 0 at the end. On the right side is 0. And mgh plus...
The first one, in the first form, the work total would be 0?
No. Delta KE, that's...
Okay, so this one hits it, and let's say the problem doesn't ask you what the velocity of the block is, but it just asks once the spring is compressed, how much does the block compress the spring? So they want to know just the X final, right? So what would you do? Work total, you would say what? What are the forces doing work on the block here?
Gravity.
Gravity is doing work, right? So it's going to be work done by gravity, and then it's going to be work done by the spring.
That's 0.
That's going to equal changing kinetic energy. This time changing kinetic energy is going to be 0, because it starts at 0 and ends at 0.
That's right.
Okay, so then work of gravity is going to be what? It's going to be positive, right? 2 times 9.8 times how much work is gravity going to do? 2 meters plus an extra amount, right? So 2 plus X final. Okay? Then what's the work the spring does? Well, if the block is moving downward, but the spring all the time is exerting an upward force on it, you see? So the spring is doing negative work. Or if I don't want to think about it, I could just use this equation. Half k x final squared minus half k x initial squared. Does that work? If I just use that general equation? Oh no, it doesn't work. It makes it look like the work done by the spring is positive, right? Yeah. No, it's negative. So that means that the equation that I had was not general. Was that the equation that I had? Half k x final squared minus half k x initial squared? Oh no, was it x initial squared minus x final squared, right?
Yeah, initial minus 5.
It was initial minus 5. Oh, okay, then I remembered it wrong. So now does it work? X initial is 0. X final is some number.
Yeah.
So the work done by the spring should be negative. Yeah. So it should make sense because the block is moving downwards, but the spring is exerting an upward force. So the work done by the spring should be negative. So this one should be 0. So then you have here 19.6, 2 plus X final minus 1/2 times, what was the K? 30, right? Is it? 30 times x final squared.
Okay.
Yeah.
Oh, this is a quadratic equation now, right?
You didn't tell me.
No, for the spring.
Oh,
Did you have it?
Is that it? So it ends up being a quadratic equation. .396 meters. That seems to be pretty large distance, huh? Yeah, from the previous. What was the K? Huh?
It was 40.
Oh, it was 40? Okay, let's just say we're using 30. I mean, it doesn't matter. That seems to be high. Well, I guess because it's 2 kilograms. But in the real world, if the spring was not that long to compress by 2 meters, it would come and just hit the ground. And then the ground would stop it, you know. Now I'm wondering if you had made a slight error. Let's say you didn't realize that this is negative. You thought it's positive. Would that give you an answer and throw you off? Let's see, what would the answer come out? Or it would give you false, no answer. So at least you would realize, okay, maybe I've done something wrong. But in some cases, you might make a mistake and you still get an answer. And you don't know that the answer is wrong, you know, so be careful for those. There's a little bit of sign that you have to take into account here. Oh, okay, you gotta say the block is going down and this is up, so there's a negative there, okay? I think with this second form, there's a less of a worry about the negatives than the first one. I'll show you why in a second. So you'll see that there's less room for error, okay? So now how do you do it with the second form? Okay, so with the second form, you say there's no external force, there's no friction, so this is 0 now, right? 0 is equal to total change in energy. So that means that kinetic energy initial plus potential energy initial, kinetic final plus potential final, right? And then kinetic initial is 0, kinetic energy final is 0, potential energy initial is what? So it's the energy that it has in the form of gravity. What's the potential energy final? The final potential energy is the energy it has in the form of spring energy. You see, I don't have to worry about a negative here. The initial potential energy of gravity is positive. The final potential energy of the spring, positive. And I don't have to worry, is the work done by the spring negative or positive? There's less of a problem like that. You set the final potential energy, you call it the original potential energy. Now I do see a room that you still might make a mistake here, because someone might do it this way. What mistake are they making? Oh, they
forgot the changing.
Yeah, they forgot the fact that this one hits this and goes down, and that means the potential energy initial you have to measure from the final position. You see, so that's probably what a lot of students will put, that one, not this one. Now, is there that same issue of forgetting that with the first form? Could you forget that with the first form?
Yeah.
Not as much, because the first form requires you to answer the question, what's the work done by gravity? Well, when it's asking you what's the work done by gravity, it makes you think, okay, gravity is doing work, and then it's doing another extra work. You see? So you're less likely to forget this. You're less likely to forget that if you do it the first way. Because you have to ask yourself, what's the work of gravity? You know? But with the potential energy way, you say, oh, potential energy initial, potential energy final. Potential energy initial is gravity, mgh. Okay, so you put 2, then potential energy final, this. Uh-oh, you forgot the extra amount. You see? So now which form is better? Well, it's again a matter of perspective. I can't say which form is better, but whichever one you decide to use, make sure don't fall into the pitfalls that are possible, the possible pitfalls, you know. So other than that, if you're do it correctly, you should get the same answer. Okay, so let's say the 2 kilogram block is released, comes down, slides here, then goes up. What's the final height that it reaches here? Okay, so it starts with a 2 meter height. So if we had a choice of deciding to do this whether in the work method or versus the potential energy, which one should we choose? I think this one, potential energy, is just better. It's just to say, okay, the initial potential energy here, right, converts into potential energy there, and then the initial kinetic energy is 0, right? Is there friction doing work? Yeah, that's the only external work done on the system. There's no other external work such as a person pulling it, right? So then you have here work of friction is equal to energy total minus energy initial. Total energy. So I'm going to do it the potential energy method, right? So then the work of friction is going to be what? The friction work done along this incline minus mu k n mu k1 n1 d1. This middle one I'll call mu k2 n2 d2, right? And then the third one I'll call this one minus mu K3 and 3D3, and total energy. Kinetic energy final plus potential energy final minus kinetic energy initial plus potential energy initial. Okay? Kinetic energy final is 0, kinetic energy initial is 0. Okay? Then what? Okay, what's the friction coefficient here? Minus 0.1. What's the normal force here? mg cosine theta, right? So 2 times 9.8 times cosine 40. What's the distance that it travels? From here to here. Right? Because the friction depends on the distance that it travels, where potential energy only cares about the height. You see?
Sine.
So the sine of 40 is equal to 2 over the distance. Right? So then that's going to be what? Sine of 40, 2 over d. So d is going to be 2 over sine 40. 2 over sine 40. So this is the normal force. This is the coefficient of friction. This is the distance it's traveled. Then this one, second one. Coefficient of friction here is 0.3. What's the normal force along the flat surface?
G.
Just mg, right? And what's the distance? Oh, they need to give you this distance. Let's say 3 meters. So this is coefficient of friction, mg, and then the distance that it travels. Minus the third one, 0.2 times the normal force there, times the distance that it travels there. Right? But then we don't know the distance that it travels because it depends on the height that it travels. Well, we don't know that either. So the only thing we know is sine of 60 is equal to what? HF over DF. So which one does the problem ask us to find? The HF, right? So then I can say DF is equal to HF over sine 60. So then I'm going to put here D3 is equal to HF over sine 60. Okay, so then you got a bunch of works that the friction is doing, right? This one, this one, this one, and then this one. What's the potential energy initial? Right? What's the potential energy initial? 2 times 9.8 times, well actually what, mgh, right? So 2 mgh, that's potential energy initial, minus potential energy final. So notice I don't have to ask the question, what's the work done by gravity? Oh, does gravity do a negative work or does gravity do a positive work? That's why I don't want to fall into that pitfall. So I just rather do it this method. I say potential energy initial, mgh, potential energy final, just mgh. Right, so then minus potential energy, hold on, I think I forgot to write final here. Potential energy final minus potential energy initial, so I did it wrong. 2 times 9.8 times h final minus 2 times 9.8 times h initial. So how do I solve for h final? Well, I've got h final here and I've got h final here. Then I have to take this, put it on the other side. So I'm going to take this, put it over there. So then I'm going to have 4 times 9.8 minus this guy, 0.1 times 19.6 times 2 over sine over cosine is tangent, right? So I'm going to write this as tangent of 40 minus 0.3 times 19.6 times 3. Then I'm going to take this to the right side and factor out the H final. 2 times 9.8, 19.6 plus, and then you got here 0.2 times 19.6 times what? 0.2 times 19.6 over tangent of 60. Okay, so then I do this, and then I divide by this. That gives me the final height. Oh, barely. 0.772 meters. Now, if there was no friction, what would have happened? If there was no friction at all on any of the surfaces, would it still go up to a height of 2 meters? Even if this angle is different than that? Yeah, right, it should. The potential energy should be conserved, right? So if my answer is wrong and I put 0 for this friction and 0 for this friction and 0 for this friction, what should I get? See what I mean? So in other words, if all the frictions are 0, 0, 0, 0, what are you going to have? 4 times 9.8 over 19.6. Right, what is that going to be? 4 times 9.8 divided by 19.6, 2 meters. So the angle doesn't matter. Angle only mattered when friction came in. You see? Okay, now, so it barely went up, right? So if that was 2 meters, 1 meter would have been here. So we're slightly under 1 meter. So somewhere here. We're somewhere there. Now when it goes back, where does it stop? Eventually it's gonna stop, right? So you tell me, where does it stop? Do it. It might stop on the level road, or it might stop on this one up here. Yeah, use the same idea.
Yeah.
Exactly.
using that
Yeah.
to see the
So, yeah, so instead of starting at 2 meters, now we're using that same. I think you should take the move around though. Yeah.
Okay, how do you do it? Anyone got the answer? Where does it stop? So it's gonna go all the way to 0.772, right? Now when it comes back down, how much work is friction gonna do? One more, another of that negative, right? So you're gonna have, let's assume that it's gonna stop somewhere on the level. Come back down and stop somewhere there, you know? So let's call this distance x. So then what would we have? We would have this guy minus this guy, right?
Right.
Minus twice this guy, right? Because you go negative, negative, so twice. And then h final would be the one we got, 0.772, right? Twice of that. Then how much work would friction do here? Going back. Then we would add minus, so that we would add something similar to this, 0.3 times 2 times 9.8, right? 0.3 times 2 times 9.8
Times x.
times x, right? That's equal to what? The potential energy, then we would have your potential energy final, which would be 0 here, minus potential energy initial, which would be negative 2 times 9.8 times 2. So it's a matter of trying to solve for x. If the x we get is less than 3 meters, then that means it stops there. If not, okay, that means it goes up the hill, you know? So we gotta solve for this x. So put it over here, take everything over there. So what do we have? It's gonna look like this, right? It's gonna have that. So this, then it's also gonna have this. It's gonna have this, right? So slightly, it's gonna be slightly different here. You have this guy, you have this guy, you have this one. Then you have twice. And then take this to the other side. And now solve for x, right? So notice I doubled this. That's important because you go here, then you go back down. Friction doubles the work because it's not a conservative force, right? So the work that it does doubles. So then you have that, then you got this thing which is the work done by friction. So now solve for x. Let's see if x is less than 3.
Why don't you account for the block sliding from the second half down?
From here?
Yeah,
Down?
as more potential energy initially. It's only
Well,
initial?
because the gravitational energy cancels itself out. You gain energy, then you lose potential energy. That one is conservative, I don't care.
Okay.
Because you see, gravitational energy, you just say, what's the final potential energy? Because he's asking, why don't you have to worry that it's going up, it's gaining energy, then it's losing the potential energy? Why? Well, potential energy is a conservative force, gravity. You see? You don't have to worry about mgh, then negative mgh.
But if we started the problem where the block is at that point,
Well, yeah,
doesn't
then
matter how it got there.
yeah, then I could do the problem all from the beginning. I could say, okay, let's assume this is where it starts. Then how far is it gonna go? I'm kind of doing it like it starts here, it goes down, then it goes down. That's true. You could start it here.
Yeah, that's how I was trying to do it.
You could.
I just redid the first problem, but with the new.
Yeah, actually, you know what? You
flip it
could.
around.
You just flip it around and do it from there. You could do that way.
Yeah.
The last two terms of the bottom equation, what do those represent?
This is the work done by friction
Oh, no,
going
no,
up.
after that.
Then another one, you double it. This one.
No. After the negative, yeah, that.
That's the work done going back. The work done by friction going this way. 0.3 coefficient of friction times the normal force
Oh, okay.
times the
Oh,
distance.
okay. And then on the other side of the.
That's the final energy is 0 minus the initial energy, which was that one. That's the initial energy. What's the answer? Anyone got it? Is it less than 3? No? Hey, don't look to those guys. On the test, your calculator, you have to look down on your calculator.
I was doing it a different way right now.
Well, no, you could do it that way.
I know,
It doesn't
but-
matter. What did you get from your way?
I didn't finish doing it.
Yeah.
When you started over, so that's I had to cross out my stuff.
No one has it? Everyone's looking at the guy next to them. Come on, guys. Test, you're gonna do it. Oh, that's good, because I was too lazy. I didn't want to have to worry about going up. We're lucky. 2.2. Okay, good. On the test, I'll give you the one that it goes back up, right? But right now, we're fine. It stops. So it would stop 2 meters going backwards, right? Cool, cool. So next Monday, I'll finish up this topic of conservative forces and stuff. So I want you to look at websites such as this, finding a potential function from a conservative force field, do a little Google search, and study up on it if you haven't had Calc 3. A little bit of fun stuff here. So they give you a force field. They show you how to test whether or not it's conservative, right? So partial F, partial X, partial F, partial Y. They need to be equal, okay? Then from there, you derive the potential energy function, right? So we're gonna do stuff like that. And then we're gonna test to see if what are the points of equilibrium. So this page was called Finding a Potential Energy for a Conservative Force Field. And the other one I can Google up is stable versus unstable. I don't know what angina is. What is that?
No.
Equilibrium. Doesn't sound good.
We'll cut that from the video.
I know, yeah. What's a stable equilibrium versus an unstable equilibrium? Right? This whole topic. So it's going to end up that stable equilibrium are points where it's a saddle point of the potential energy function. And then if you displace it, it goes back to that equilibrium point. So it's really a calculus topic. Like, for example, this is unstable equilibrium. You see a pencil that's leaning on its, this is unstable equilibrium. If you do it just right, it could stay there. But if you displace it from that, it will fall. How about an egg on top of the roof? Is that unstable equilibrium? If a rooster lays an egg on the top of a roof, which way does the egg fall? That's a riddle. You know what that answer is? Roosters don't lay eggs. Okay. So what is an example of stable equilibrium then? Oh, they have another word for it too. Endemic equilibrium and epidemic equilibrium. Wow. Oh, I like this. They're applying it to some ecology examples. Detection of stability is not that simple in one variable models. Let's consider a predator-prey model with two variables, density of the prey and density of the predators. See? Dynamics of the model is described by the system of two differential equations. dH dt is F, dP dt is G. In other words, if the prey increases in, increases in magnitude, the rate of death of the, if the predator increases in magnitude, the rate of the death of the, okay, whatever, however you say it, the prey dies, right? Then they say second step is to linearize the model at the equilibrium point by estimating the Jacobian matrix. Woo-hoo-hoo. Third, eigenvalues of matrix A should be estimated. Oh my gosh. Eigenvalues, saddle points, unstable focus, unstable knot. And Alan's just really enjoying all this lecture now, you see? Stability in discrete time models. So very interesting topic. Of course, we're not going to go this detail. We're going to do very basic stability models, but you can see there's a whole model in it. The whole topic opens up. Pandora's box opens up. Unstable, stable, stable. You can check this yourself by using Excel spreadsheets. Oh wow, a lot of mathematics behind it. Nice, isn't it? Okay guys, so see you, tomorrow by the way, your lab 7 is due, the circular motion lab. Remember, it's not a write-up, so you just have to finish it. Okay, see you guys tomorrow.